So, wait, let me start my backup voice recording thing here. Okay, so good morning. So my name is Brad Miller, and I'm over at WPI in the Robotics Engineering department. And so I'll have to do a plug here because they're like paying for me to be here. If any of you guys are like interested in doing robotics, like you're doing it now, and you want to keep doing it after you graduate from high school, you can keep doing robotics engineering, get a degree, and the highest paid starting salaries of any of the 54 majors at WPI was for robotics engineering majors. So it's not just, so you can turn, so when they say it's not about the robots, when they're talking about it, well, it can be, and you can do really well. So yeah, so if you have questions about WPI, come up and ask. I guess, so my background just a little bit is somehow I got roped in by FIRST to work on WPI Live back in 2000, well, we started in 2008 for the C Rio, writing the software libraries for it. So I did this C++ library, and then it kind of expanded after that. The next year we got Java. I kind of figured out that it was a school, so students were supposed to do the work and not me. So next year we had a group of students do the Java port. But since then, it's grown and grown, and we've had more and more people getting involved in it, and in this whole project. And so right now, it's barely me. I mean, I'm barely doing anything but writing software. But one of the newcomers to the project, well, not that new, like 4 years or something? 5 years. 5 years, is Peter Johnson here, who some of you guys may have interacted with if you've had issues. Did the camera server, all the camera server stuff, the CS core stuff and all that, and he also did network tables, or a rewrite of network tables to make it much more efficient, and kind of he's kind of the steward of that. So he has been doing like awesome things, and there's a bunch of people who can't be here but are working on new things. So there's a big group, and so I'll say that as you're using the software, if you have any problems or issues or you can't figure out stuff, all of our stuff is all open source on GitHub, and you guys can go to the GitHub repository and you can put up post issues or ask questions and that kind of stuff. So yeah, so we're here to help and help you make things work better. And we have a special guest star here that happened to be at the championship, Greg Hellstrom, you guys may have seen the Limelight camera. Some of you may have seen it, which is a really, really good way of getting into computer vision. And he'll talk more about that and do a demo of it, but it's a pretty cool thing that he's come up with. So what we're going to do today is kind of do an overview of kind of what's going on with computer vision with respect to FIRST, what was new for 2018 for this past year, and so I'm going to talk about a bunch of cameras, like different options for cameras which you can use. We'll talk about kind of how you program using the libraries, how you write programs for the robot, and get all that stuff to work. We're going to talk about grip, which some of you guys have experience with, and then we're going to do this really cool end-to-end demo. A lot of people found that they want to run their vision code not on the Robo Rio, but somewhere else. And so what we've got up here is a Raspberry Pi and a Robo Rio and some cameras, and we're going to show you how to get. They're over there. So we're going to talk about how to do this. We'll do this end-to-end demo of how to use it. Plug a camera into a Raspberry Pi, get the data over to the Robo Rio so your Robo program can use it, and so that's kind of nice. So that's what you'll see. Just as an overview, so one question is, like what's computer vision, or what's this all about? And FIRST kind of goes out of their way very often to add things, elements to the game, into the field, to try and kind of entice and challenge students on teams to be able to find goals autonomously, do aiming of shooters, all that kind of stuff. But being able to find those things is not trivial. I mean, nobody says, go forward 10 feet and turn right and you're there. You kind of have, the robot has to be able to find targets and aim at them and stuff. Some of the older games, like in 2006, was pretty interesting, where you had to shoot balls through a goal. The goal had a round retroreflective tape. Oh no, that was actually a different one. That one had the cold cathode light on top of it, this green light, and you looked for the green light with a camera, and then you shot balls in. There's been new versions of that where people are just using, and that was using Pixie Cams. There's new versions of that have come out now. So you're using retroreflective tape with cameras and ring lights and all that stuff. People this year were looking for cubes with cameras to be able to do the multi-cube autonomous stuff that you see. So so it's really so computer vision is a huge field. I mean, it goes way beyond FIRST, but you get a lot of really good experience doing this stuff for FIRST teams. I mean, you can imagine the problem. One of the biggest problems in robotics, you talk about robots, and you say, well, robots are things that read sensors, read the environment, then do some computation, which you can kind of call perception, where the robot tries to understand what's going on by the data that comes in from sensors, and then act on it, driving actuators and stuff like that. So you probably, you can imagine, these days there's lots of companies who are working on autonomous vehicles, autonomous cars, and those things are loaded with sensors, in particular lots of cameras, and they're doing all kinds of crazy vision stuff to be able to recognize stop signs and people about to walk out into the street and stuff like that. I actually was fortunate last year, before they announced it, to be over at Uber and be able to ride around the streets of Pittsburgh for like 20 minutes in an autonomous car. And I was sitting in the driver's seat, and they said, oh, just hold your hands over the steering wheel and get ready to step on the brake, but don't do it unless you need to. And I never did. I mean, 20 minutes, driving around all over the place on a Saturday morning where the streets are like really crowded and there's people walking around everywhere, and stop signs and traffic lights and everything. And the computer is using lots of sensors, but one of the primary things it's doing is computer vision, where it sees this stuff and it has to be able to understand it and figure out what to do. So you guys are getting like this really good start in playing with computer vision and being able to understand that stuff. And I keep seeing more and more sophisticated things that people are putting on robots. So pretty cool. So keep doing this. So you kind of talk about this, this is kind of like a combination of photography and a lot of computer processing, computer science stuff. One of the things you need to make this stuff work is to have good images. And so you have to have good exposure, good lighting. One of the things that we do to make that easy, okay, a lot of the FIRST targets have this retroreflective tape, right? So you know what that is. It's like, that's like the stuff that they paint highway signs with. So from whatever angle your headlights hit it, the light just reflects back at you. And so if the trick is you have a camera, you turn down the sensitivity of the camera, you put on this super bright ring light, like a car tail light thing, and you blast it. And if you have a camera here with the ring light and you look like this and you look at the target, it just looks normal. And as your head approaches the view of the camera, you start getting all the light just coming back in your face, and the thing just pops. And all you see is the target. You don't see anything else. So it's important to have that kind of stuff, to have good images. Otherwise, you really can't do any of this. And then you have to be able to process the images and figure out what to do. But it's really not okay. So this isn't magic. I mean, there's very well understood kind of mathematical ways of doing this image processing. There's lots of software libraries around. So as an example, you might say, well, what is it, if you're trying to describe to somebody, like, what is it about the target? Like, what makes it unique, and how do we find it? And like, what do we do? You might try and describe it. You might quantify, like, what the target looks like. And so for computer vision, some of the things you might look at are like the color of the target, which kind of depends if you're using a ring light, what the ring light is seeing. If you're using a camera looking for yellow cubes, it may be the color there. The size of it. The size is actually really important, because as you get closer to it, it gets bigger. And if you know what the size is, and you know how small it looks in the camera frame, then you can figure out how far away you are. okay, by doing some very simple trigonometry, you know, that most high school students can figure out. Then there's a bunch of kind of more sophisticated, you know, kind of computer vision-y kind of tricks. So one of them is, there's this thing called the Convex Hull, which you can do for an image, you know, where you get a bunch of points that define the image. So imagine if you took a string and wrapped it around all the points. It's kind of the bounding box that goes around all of the points without having any concave surfaces. And you take that and you take the area and divide them and you kind of get some ratio of the solidity of the object that you're looking at. So you can tell whether it's a, you know, U-shaped goal or if it's just this blob of reflected light or something like that. So there's lots of things like that. You know, the aspect ratio, like, you know, you look for targets and it's supposed to be square, but you found something in the image that's, you know, really, really wide and short. So you go, oh, that's not it. You know, and you go look for other stuff. And then there's a bunch of tests that people do, you know, like for testing, like limit tests, right? So you say, well, there should be two pieces of tape side by side, and they should be about, you know, this tall and about this wide, so you kind of know the aspect ratio of each one, and you know the position relative to each other, and so you can say, oh yeah, that's the target that's in front of the peg that we have to, you know, that we have to put the gear on, and so you can do those kinds of tests to help you decide which things are targets and which things aren't. Yeah, so here's some examples of what this is what happens with the ring light, right? Where you have the ring light lighting this stuff up. These things just pop. This is a strip of lights. They just put this in to make it harder for us. But this is a strip of LED lights going up and down the thing, which are close enough to the, you know, which are really, really bright. So here's a ceiling light. Here's this stuff. But then you get these things, which are specifically this color because the ring light was that color. And so you could look for the color of that, and you could throw away all this other stuff. And we'll do an example of that, or at least one example, a little bit later. So kind of like the workflow, you know, like what you do, we try and make this so it's easy for you, you know, so you can do this stuff. So one of the things that we do is like about, you know how you watch the recording of the kickoff, you know, you know, at 11 o'clock on Saturday, you know, in January. That recording was actually made like a month before. And so when the field's all set up and everything is nice and clean and working and it's the final version, we take pictures using a camera, using a ring light of all the vision targets and all the stuff that might be interesting. And we put hundreds of pictures up on the web so that you guys can grab those pictures, and on the first day, okay, at noon on that Saturday, you can take those pictures and you can start working on vision code, because it's what the stuff will look like with your camera on your robot. Because we do it from different heights and we do it from different distances, and we kind of tag the images with all that information. So kind of a good workflow is to get going right away. I mean, you know, if somebody on your team is interested in vision, at 12:30 on the Saturday of kickoff, they can be on their way. Okay, and then in the meantime, you start building real goals and real targets, and you start building your robot and all that stuff. But you're like 80% there, you know, long before you've built any of this mechanical stuff, and you really can start figuring it out. So you can do this design of the vision program, and then once you get that working, then you can stick it on the robot. And then you can add the stuff for the robot to steer it and do whatever you need to do, you know, drive the actuators based on the vision. So the workflow, what we recommend you do is take those images that are put up there like really early, and then go to town and start figuring out this stuff. And just do it on your laptop. I mean, everybody has a laptop. Everybody can just take this stuff home and play with it. You can be sitting on a couch watching TV, and you can work on your vision program. And you don't have to be in a lab. You don't have to have any special equipment or anything. Oh, by the way, if you guys have questions, just yell, okay? I mean, this is way too long to wait for the end.
What's your website?
The website is, what was the website? Like the Eclipse plugins comes from first.wpi.edu, and there's a directory on there, and it's on Screen Steps. You know, it says where the stuff is.
Yeah, Screen Steps would be the best place to.
What?
Screen Steps is.
Screen Steps is the best place. You guys all know about Screen. Does anybody not know about Screen Steps? Oh, good. Okay, no? Okay. Okay. WPILive.screenstepslive, L-I-V-E, you know, screenstepslive, one word, .com, is where all the documentation is. And it tells how to work all the software. So your homework is to go figure this out. But that's where you'll find all this information and the link to all this stuff. So, and here's just some examples. I mean, these were from the images that were posted. So there's a target for gears, and here's the game. What was the Frisbee year? That was whatever year.
2013.
Yeah, so there's that. This is the medicine ball one? No, oh, yeah. Okay. And then this is, Stronghold, yeah. So that's the top of the castle. This is good, yeah. So that's what those things look like when you're in the dark, which I think I am usually when I'm. Okay, so we'll talk about. So we want to talk about some of the 2018 stuff and like what we've done. So the first thing, I don't know if we actually particularly talk about this. One thing is, so I'll just mention this. One thing is that Peter spent a lot of time last year over the summer and through the fall working on camera server to make it, the camera server stuff to make it very, very reliable. That's the software that you use in your robot program or on a coprocessor or something to be able to capture the camera images, do the stream and deal with it. So that's like pretty solid, and he'll talk more about it. But I just want to make sure that that was something that we did this past year. So the one thing I want to talk about is Opencv. In the past, up until a couple of years ago, we used NI, the guys who do LabVIEW, have vision libraries, which people use a lot. I mean, they're used in industry, for all these, LabVIEW things and for, kind of pick and place robots and for, stuff going by on assembly lines and all the automation stuff that they do. But what we kind of looked at that and it was working, but it really was designed to work with LabVIEW and not really designed to, and it was not really well documented and stuff. So we kind of made the decision to flip to Opencv, which is the Open Computer Vision Library, which is actually what people use in universities. I mean, and that's what people really use for doing stuff. I mean, it's very, very, it's ported to, all platforms. There's bindings available in lots of languages. And so we kind of changed everything to use Opencv. We made a version of it for the RoboRio, and it's kind of bundled with the software, so you can just call Opencv stuff from your robot programs, and it kind of works. And it runs on anything. I mean, it's really good. And it has this like huge, one of the things that was really good about it was, this is from last year, I guess. So last year, at this time, there had been like 47,000 people using it. They had like 9 million downloads of Opencv. So this is like, I mean, that gives you an idea of how huge this is. I mean, it's really what people use in industry. And so, so I think this is something that if you use it in high school to build your robots, you go to college. I mean, this is what you'll study in college is Opencv and doing vision algorithms with it. What I want to do now is turn this over to Peter, who's going to talk a little bit about camera options and other things. We're going to do this like kind of tag team thing.
We'll tag you. Yeah.
So.
Good morning. Yeah, so just walk through some of the different camera options. Certainly there's a lot of cameras out there. The Axis camera is very popular. It's actually become a little less popular since the USB camera support has improved. The Axis camera is just what used for security cameras. So it's a pretty decent webcam, just hooks up through Ethernet. It's a little annoying because you have to tether it through the radio, which means that you don't have any open ports on your radio anymore. You have to put it on an Ethernet switch or something like that to get access. And the price point isn't that great for many of those IP cameras. Usually, like the Axis camera is retail a couple $100s, so it's not super cheap. What a lot of teams have started using in the last year or two is USB webcams. So these are your little Logitech or Microsoft webcams. Typically run in the price range of $20 to $60. They just hook up through USB either to the RoboRio or to a coprocessor. Really cheap. Now, one downside of them being really cheap is that they don't have as many options for tuning, right? They're a little bit restricted on that front. Sometimes the frame rate isn't that great. There's limited frame rate ranges as well as resolutions. Sorry.
Compatibility's been an issue for me with different webcams.
So generally speaking, compatibility is pretty good. This year, There's been some change, particularly with the RoboRio, there's been some changes this year where there was a couple of things that were broken on the RoboRio compared to last year with USB webcams. They do generally work. You may just need to choose a different resolution or something like that with them. But you're right, it's sometimes a compatibility concern. Basically anything that's compatible with Linux should work, but the RoboRio's had some issues this year, I'll admit. A couple teams, not so much, I don't know if many teams did it this year, but last year a number of teams used cell phones. So they literally wrote an app on a cell phone, you use the cell phone camera, and then it's a little tricky because how do you hook that up to the robot then? You have to use like a USB to Ethernet adapter and do a lot of work there. And it's also a little expensive. I mean, depending on the cell phone you use, an Android cell phone is going to set you back, $100 to $200 type of range. USB 3 industrial cameras, very expensive, very high performance, very nicely packaged, many different frame rate options, but a little on the pricey side. We don't do a lot of work with that in FIRST, mainly because we don't need to. As Brad was saying, a lot of times the image processing we need isn't all that. It gives you a slightly better image, you have better tunability, but for the types of things we're doing in FIRST, it's not really strictly necessary. Pixie Cam is a little compact thing that hooks up with serial port. You can kind of tune it to different parameters. It doesn't give you an image back, so it's kind of, if you want to use it just for like a display on the dashboard, it's not great for that. But if you just want to track to a target, it's pretty good. And then some other options like the Limelight have emerged recently, where it's a very canned solution, a little bit more expensive, but is much easier to use, right? So what you're paying for is the development time that they've put into it to make it a packaged product that's easy to put on a robot. So I guess I have some charts on these and kind of go through. So IP cameras support multiple clients. It's really easy to hook up to a web page, stream on your dashboard. It's a pretty basic configuration with a fixed lens. USB web cameras, again, kind of huge quality range and price range. I mean, they make 4K ones, like complete overkill for a robot, and you're going to kill your processor trying to actually process something like that. So now, the whole reason I wrote Camera Server was basically it lets you make any USB camera into an IP camera, either through the RoboRio or through something like a Raspberry Pi. They are a little tricky to mount. They're really designed, I mean, when you look at most of them, and you're like, how do I mount this on a robot? It doesn't have screw points, it doesn't have, I have seen teams actually take it out of the case, and sometimes they have little screws inside or some way to mount it. I've seen 3D printed cases but getting the alignment 100% correct is a little tricky. There's actually a number of USB web cameras which come unpackaged. I've got one sitting on the table over there where it's just like, that's on Amazon for $50, and it's a 60 hertz, 180 degree field of view lens on it, and it's got 4 screw holes. Like, okay, I can mount this, and it's USB, so it works with other stuff as well. So typically, though, they have fixed lenses, not replaceable lenses, so you kind of have to buy what you want, or you're limited to what the camera comes with. Cell phone cameras, as I mentioned, write an app. Pretty good software support and documentation because lots of people are writing Android apps that talk to a camera. There are lens adapters available in some cases for these, because people like to take selfies and do crazy things with cell phone cameras, so you can find adapters. But again, kind of the challenging, just like USB cameras, how do you mount this thing on the robot? Like, okay, are we unpackaging our cell phone? Or are you mounting a 3D printed case? What's the solution there? Yeah.
Oh yeah, I just wanted to also add something for cell phones. Any guys do FTC? Yeah, so you guys are using like cell phone cameras and Vuforia. So there's some really interesting stuff going on in FIRST where this Vuforia program uses cell phone cameras and with Android, and they can find targets on the field and be able to figure out where they are, where the robot is, like what its heading is and where it's located. So there's some really cool stuff. Maybe you'll see that in FIRST sometime, or at FRC sometime, but it's another good use of cell phone cameras.
Yep. So Pixie Cam, so that's a camera with a built-in processor. Again, very limited capabilities, but it has different output types. You can hook it to the RoboRio and just get, hey, it's at this direction, this resolution, this distance away, and it's a 50 hertz camera, so it's a pretty fast response, low latency solution. Yeah.
Being that with Pixie Mod, you get the image on the Pixie Mod.
Right.
Is there a way, you get source code to Pixie Mod to be able to get the image back out and
I've looked at it in the past. I haven't taken it all the way to get it integrated with the rest of the libraries. Basically, with the wide availability of USB cameras, we haven't done a lot of work on Pixie Cam, but certainly contributions are very welcome on that front. So I'll skip the video, but USB 3 industrial cameras, so machine vision, like things like visual inspection when you're on a manufacturing line. Like I'm building 1 million parts, I want to take a picture of each one as I'm manufacturing it. So they're very designed for high quality images. There's a couple of them that have started to become FRC priced. Oftentimes these things are in the $1,000 range, so well outside the realm of what's legal for FIRST, but there are some options that are becoming that way. On the RoboRio, of course, the RoboRio only has USB 2, so that kind of limits things. There are good software support and documentation through, there's a software stack called GenICam that talks to these things. There's Ethernet industrial cameras too, and basically what this allows you to do is very rich configuration, high performance. In my opinion, it's kind of overkill for FIRST. Usually teams are fine with something that's lower priced and a little bit easier to work with, where we have kind of the built-in software support. That's why we did the software, is to make it easy to use cheap things from the USB camera perspective. So some examples of specs, like the Basler Dart has a global shutter, so you can control the shutter. It has 50 frames per second in color, 120 in black and white and full frame. So you can do even higher frames per second if you're doing a partial image. I mean, hundreds of properties. So again, very powerful. Particularly when you go into college type of robotics, these are the types of cameras that you'll be using. But I think my personal opinion at the first level is that this is overkill for what we're trying to do in terms of image processing. So hardware processing, so what are the options here? So you can do on the RoboRio, you can be running Opencv. RoboRio isn't a very powerful processor. It's a dual core ARM, kind of a 7 years ago cell phone. And it's not going to be able to process very high resolution camera images. It's not going to be able to process them at a very high frame rate. And the frame rate is something you care about, in particular the latency, how fast you get that information to your control systems on your robot. Another option here is, of course, the driver station computer, kind of a little latency limited. You've got the camera image has to make it from the robot to your driver station computer. Your driver station computer is very powerful in comparison to basically almost anything running on the robot. But the downside is that it's high latency. You got to get the image to the computer, process it, send the processed data back to the robot. You're talking about network latencies of tens of milliseconds typically. So it's very powerful on the processing side, but high latency. Yeah. Oh, sorry. Question.
Is there a way to use? I mean, you're already streaming the camera to
Sure.
the driver station. Is there any way to use that as well to process?
Absolutely.
Okay, so you use the same.
Yeah, you can use the same image that you've gotten to process. Yep, and show it. So like, for example, the shuffleboard application is a Java application. It's easy to write plugins for it, so you can write a plugin that does the image processing and sends the data back to the robot. Absolutely. More popular is onboard coprocessors. In terms of, if you run out of processing power in the RoboRio, or hey, all I want my RoboRio to do is just run my robot code. I just want to be able to drive. Anything beyond that, let's put on something separate. Not a bad design choice, because there's lots of options for onboard coprocessors. Raspberry Pi, Kangaroo is an embedded Windows machine. It's the middle picture there. There's much more powerful ones. The NVIDIA, big boards, TK1, TX1s, cell phone, and then things like the Limelight, which uses a compute module to do the heavy lifting on the image processing, and again is a easier to mount solution, kind of more canned solution. And of course, many others out there. So let me talk real briefly about camera server. So the idea with the camera server library, which I also call CS Core, is really, again, to make cameras easy to use. So it's got a source sync model, so you can have multiple cameras. You can take the image that you get from a camera, send it to multiple places. You can do you can pull it into Opencv and show it over MJPEG stream on an HTTP stream. And you can switch syncs between sources. So you can say, oh, my image processing needs to pull from 2 different cameras. Sometimes I'm driving this direction, sometimes I'm driving the other direction. I have 2 different cameras, and I want to switch between those cameras, and it lets you do that. Because you say, oh, I have 2 sources, I switch between them. Similarly, like to the camera feed to the driver station. Maybe you want a higher resolution, but you run out of bandwidth, but you only care about seeing 1 camera at a time. So you can switch between different views that you're sending out to the driver station. So it does support both USB and IP cameras. It is multi-platform. I will say at the moment we're limited to Linux for USB camera support. That is something that I kind of planned on doing last summer, but ran out of time to do. And really, because I do want to have it work with USB cameras on a Windows laptop or on a Mac laptop, just work out of the box, mainly for simulation. One downside, one thing that no matter what I do on the library side is going to be limited for those cross-platform support, is that the camera settings on different platforms is different. So that's something that I'll never be able to fix on USB cameras because the drivers are different on different platforms. So it may be more common to Mac, but certainly to Windows. Like if you set brightness settings on a USB camera on Windows, it's going to be different settings than on a Linux platform. But just having the support there so that you can run your code is a good thing. So it does, again, let you set the camera properties if the camera supports it, clearly. So brightness, exposure, frame rate, frame size, the resolution. Most cameras have some, you can set the color temperature, other things on it. And one of the things that the camera server library does is it gives you a web page access to do that. So you can pull up a web page, you can just type in the IP and port number, and it gives you a streaming view and settable camera properties. And one of the improvements I'm planning on making next year for this is more support for, like, oh, I want to just change the video mode on that view and get a different, allow you to experiment live and then save those settings to code. So it's one of the things that we do with at the camera server level is it automatically creates that streaming JPEG server when you create the camera, and it publishes information about it to network tables. And that's how things like Smart Dashboard, Shuffleboard, the LabVIEW dashboard, where it gives you a drop-down or a list of cameras, that's all published through network tables, and that's what this library provides. And it does work on coprocessors too. And the idea with this is that every coprocessor or the RoboRio or whatever has a camera publishes information about it to network tables, and that way it just appears in a list, and you've got kind of an enumerated list of different cameras you can choose from, and each camera is named. So one of the fancy features that very few people know about is if you have an access camera and you add it in your code, it actually mirrors it to the USB port. Not only does it add it to the camera list, but you can tether through USB, and it'll restream the access camera stream, so you don't have to worry about plugging into that extra Ethernet port.
Oh, question?
Yeah. So network tables, that's really I'll talk about real briefly here. Basically, we added some APIs to network tables this year, so we created new APIs, and we deprecated the old APIs that were still perfectly valid to use. So you can still use the old APIs and talk to it the same way you always talk to it. We just created new APIs that make it a little bit more kind of easier to use and more performant going forward. So it's really at your option what you use. It's not like the old stuff was broken. So.
But when you see something that says it's deprecated, that means it may go away like in a future year. That means we're switching to something new. Consider switching yourself. But for the time being, it's there.
Yeah. So some brief code examples. Again, the whole concept with camera servers is to make it easy to use, right? So if you just want to stream, your vision to your dashboard, you put a camera on the robot, you want to see it on the dashboard. You just run start automatic capture, and it looks for a USB camera, and it puts the first USB camera and publishes it. You can support multiple USB cameras. So if you have like a front and back camera, you can use different device numbers. That's what the 0 and 1 are. And the one downside of the 0 and 1 option is that basically it depends on what order Linux enumerates the devices in when the robot starts up. And if you unplug and replug in different cameras, it may not necessarily always come up with 0 being 0 and 1 being, in terms of port numbering. There is actually a way to specify an absolute camera path, and what this uses is the what's called the dev v4l, so video for Linux, the path in Linux, there's actually a by path section of that, which if you put in USB hubs, it changes the path. So every port is differently numbered. So this example here, where it has the platform dash whatever. The only actually part that changes this is an example from the Raspberry Pi. The only part that changes is actually this 1.2. So different ports are like 1.3, 1.4, 1.5. And so it's actually possible to lock a camera server instance or camera server camera to a particular physical Ethernet or physical USB port. And that way, okay, if I plug stuff into the same ports, physical ports, I'll get the same cameras in the same spots. So that's kind of useful from a reproducibility. Yes? Yeah. We'll publish the slides.
Yeah,
Yeah.
yeah.
Where would that be?
You know what? Look at the first page of Screen Steps, and we'll put something there that says where some of this stuff is.
Okay, cool. Is there a way to check to see if there's a camera plugged in before you try to instantiate it? Because as soon as you instantiate it, then like even just running start automatic capturing.
Right. I mean, all it's doing is the whole design, the design is such that, yeah, it's going to print a message once a second that it can't connect to the camera. I mean, it's not going to flood your output. I mean, 1 per second isn't ridiculous. Right now, there's not. That's one of the feature requests I've gotten this past year. So that is something I'm planning on adding this coming year. It's simply maybe not so much for the detection, but at least to be able to turn off the message if you don't care to see it. Yeah.
Unrelated, but I've heard that there's ways, you talk about like interfacing with USB, this whole path.
Mhm.
There's ways that we can write files to a USB using something that we got speak, but I haven't been able to figure it out.
You're talking about like a USB stick or something?
Yeah.
So that's kind of a little outside the scope of this talk, but yeah, you can, if you plug in a flash drive into the USB into one of the RoboRio ports, it automatically mounts it. So you can write data to a USB stick just by, I think it's /U, I think is where it automatically mounts it to.
/U doesn't work. Is this path anything related to that?
No. This is solely about USB camera devices. Yep. Another thing again that supports access cameras, so you can add an access camera. This actually does accept a list of different IP addresses. All of the camera server stuff is designed to work with multiple IPs for anything that's IP based. For example, what actually gets published in network tables for your automatic capture, it actually publishes a list of all the different URLs that you can get to the camera stream. And the reason it does that is because you can reach the RoboRio through a bunch of different IP addresses. I mean, it's the IP address that it's connected as, the USB, other things. So it actually publishes a list of it, and then on the client side, we basically try all those at once and say, oh, let's try all those in parallel. Whichever one connects first, we'll go with. So it's all designed to make it as robust as possible for teams to connect to the camera. Right. That's the whole point of the library. Again, camera settings are also exposed to software, so you can set the video mode, set the brightness, white balance, hold current. So there's some built-in ones. One thing I didn't include on this chart, but is certainly in the library itself, is the library. These functions are for specific, well-known camera settings. It actually supports all camera settings. Anything that the camera exposes to Linux, that the Linux drivers expose, is exposed through camera server just with strings. So you can do set property with a string, and the strings are dependent on the camera, but they're shown on the web page. So if you go to the web page, you can actually see, oh, okay, it's this setting, and you can put that setting then in your code. One improvement I'm looking at doing for next year on this is actually, making it so it's easy to like persist camera settings. So you go to the web page, you have a set of camera settings, you go save that as this JSON file, then you can copy it to the robot and load it. So that way it will be a little bit more easy than manually putting stuff into your code, which is what you currently have to do. I'll do a quick demo here with just the RoboRio camera server. It will take just a couple of minutes. How are we doing in time, Brad?
Oh, I think
Yeah, we're fine.
it's 9/11. So.
Okay. So what I'll do is I'll hook up a USB camera. So I've got a RoboRio here with a USB camera hooked up to it, and I'll go ahead and tether it here so I can talk to it. And I'm going to add the line of code to the robot code, and then I can view the camera. The other thing that Camera Server, of course, does is it also exposes it to Opencv. So you can also take the same camera that you're sending to the driver station and process it local to the RoboRio. Yeah.
Running on the RoboRio, you mentioned being an older architecture. What about performance? And you start having vision on there, streaming or...
Right, so, yeah, the big thing on the RoboRio is, yes, it's an older architecture. It's an ARM v7, about 700 megahertz. What is possible to do is low resolution. So the biggest way that you can save on processing time, and this applies to coprocessors as well as any other type of image processing, is if you can crop the field of view, if you can reduce the resolution so that you're processing fewer pixels, everything is linear with the number of pixels. But the number of pixels, when you go from a 160 by 120 to a 640 by 480, that's not just like, that's a huge, it's exponential number of pixels. And so what you really want to do is get to a point where you're processing fewer pixels, whether that be, hey, I do a couple of image processing steps and then I say, oh, I'm interested in this region, and you zoom in on that region and do the rest of the processing steps just on that region of interest. That's a very common technique to use. But yeah, you're right. It's going to be limited in resolution and frame rate compared to coprocessor solutions.
We've had very good luck running on the Rio. Worked well for us.
Yeah, and you're probably running 320 by 240 or 160 by 120, right? You're running a low resolution, but it's good. It's one of those things where it just runs and it works, and you don't need any extra hardware. You just plug in a USB camera and you can do it that way. So there's advantages and disadvantages. So it's a trade-off, as with most things we do in FRC. So, all right. So let's real quickly jump out here, and I've got Eclipse up with a robot program. So this is just the template robot program. The only line of code I actually added to it, hopefully, sorry, it's a little bit of an eye chart. How do I zoom in? I guess what I probably want to do is actually change the resolution. Control plus in Eclipse. Hey, look at that. Thank you. So this is Java. It does work in C++ as well. Basically, the way that the WPI libraries are designed is that the C++ and Java are basically exactly the same. The only thing that changes is you have to use pointers in some places, and the functions all have a first capital letter instead of a first lowercase letter. That's really the only difference between the two. So when you see an example, it's very easy to translate back and forth. The only line of code I added here was just this line of code. So this camera server, get instance started on capture. If I go and run this robot program, oops. So hopefully it's hooked up to the, yep, it's hooked up to the robot here. And so it's already up and running, and what we can actually do is, what this does is actually a couple of things. And I'd like to show first, interestingly enough, is actually it puts up a web page. So one of the things that this does is that, so I've got the robot on fixed IP, but it puts the first camera at port 1181, and I can go straight and start viewing the camera. So without even a dashboard application, I've got got this as pretty high frame rate, and smile for the camera. No, pretty high frame rate camera hooked up and streaming directly just to a web page. And this web page is very useful because one of the things I can do with it is just start playing with the camera settings. Like, oh, it's too bright. I need to increase the contrast or decrease the contrast. And turn off all things. And then this other thing is that it does let me look at what all the different video modes are. And so it's got this big long table of video modes, and this list will depend on the camera you have. So this camera is a little ridiculous. It supports up to HD type of images, 1280 by 960, and it supports multiple pixel formats too. So it supports what's called YUIV, which is a uncompressed video format. It's sometimes good to run in a YUIV format if you are doing image processing, because the reason is that basically that means that particularly on a RoboRio, you don't have to decompress the image. So the camera doesn't have to compress it, which means you're getting it faster, and you don't have to decompress it, which also means you're getting it faster with less processing power. Yes? So it does not. There's no capability within the RoboRio processor for the actual video codecs. It does have like neon and some of those accelerations, so it is possible to use those to accelerate certain image processing steps. Opencv does take advantage of that where it can. Yeah. In which? Yes. Yeah. So the Python Robot Pi also has wrappers for camera server, and they work basically the same way. Yep. Well, the other way to do this is RoboRio team number FRC.local port 1181. So the 1181 is the port. So when you look at like the rule book, port 1180 through 1189 are reserved for cameras. The camera server class, when you create the start automatic capture, it puts the first camera at 1181. If you create another one, it puts that one at 1182, et cetera. So this just gives you the long list of video modes, which you can change this year in your code. I think next year I'll make it available through the web dash, and lets you change the camera settings. So as I said, it kind of gives you that instantaneous feedback about different camera settings. The other thing it does is it does publish it so that you can view it on the dashboard too. So what that lets you do is if we run like Shuffleboard, for example, I'll come up here. It's thinking. Or I'll start a smart dashboard too. Start up both, just for, so if you do add MJPEG stream viewer or camera server stream viewer, when you look at this, you can, oh, I need to connect it, sorry. Fun of live demos. Help if I actually set the team number correctly. Okay, so what this gives you, so one of the things that this puts on here is this USB camera 0, how this drop down comes is broadcast by the robot. So and that shows up in network tables, and one of the things in network tables, if you run this tool called Outline Viewer, it lets you see all of the different things being put in network tables. And so this is the camera publishing that I talked about. So it puts, for every camera that you create, it creates a whole tree structure under Camera Publisher that has all of the different properties, as well as a list of so it has like exposure, contrast, power line frequency, all these different settings, and it provides a list of modes. It also gives you whether or not it's connected, which is kind of a useful thing to know. And it gives you a description, what mode it's currently running in, and this is the list of streams. So again, this is how we know, okay, it's trying a bunch of different IPs. It tries the .local, it tries the hard IP, it tries the USB camera address, et cetera. And it also lets you know where it's connected to on USB. So that's an example of just streaming it to the dashboard. Now, what's nice about this is that then you can go and take this capture and start doing image processing on it. And we'll talk about that next. I'll hand it back to Brad to talk about grip. But you know, here's some code that I have running on the Raspberry Pi side of it. There's this thing called Vision Runner, which is in the WPI libraries. And if you create something in grip, you can just pump the camera into that Vision Runner and run the grip pipeline on it. And you can do that on the robot. You can do it on a coprocessor. The code looks the same. This example code is taking the grip pipeline and the camera that we've created with Start Automatic Capture, and just then doing some image processing on it that we set up with grip, which Brad will talk about again, and then putting that information in network tables. And of course, on the robot side, you can decide either to put it on network tables, or you can just directly feed it into the rest of your code. So with that, I think I'll hand it back to Brad to talk about grip a little bit. So let me go back to the PowerPoint and make sure that's where we're at. Yep. All right. So did you want to bring over your laptop, Brad, or how did you want to do this?
Let's do aren't there some, there's a few slides first, right?
Oh yeah, there's some slides first.
So let me do those now.
Okay.
Then we can switch. Okay, so I'm going to talk about this tool called Grip, which you guys should at least try. I mean, you know, I think it's pretty cool. You should play with it. It's easy to do, and you can do it in the off season. This was so it happened. So everybody at WPI has to do this like you know, senior capstone project, and so a couple of students who came from first teams wrote this thing called Grip, which is so you know, whenever you do vision processing, we keep talking about this. But you haven't really seen it. Whenever you do vision processing, there's usually a sequence of steps that you do. So you grab the image and maybe make it smaller, and then maybe you filter it somehow, or you do some thresholding on it, or you do one, you know, then you do something else, and eventually you figure out where the target is. And so Grip does that graphically, so that you can just drag and drop image processing steps to make a pipeline, and at each of the steps you can see what's going on. So, and it's all built on Opencv, so it's pretty good. We've had lots and lots of first teams use it, well, as you saw, and we even have researchers using it, you know, for you know, for university level stuff. And it works, you know, with like everything else we have, it's cross-platform, and you can use it with any language. The user interface for Grip, and we'll do a demo of it in a few minutes. The user interface of Grip kind of looks like this. This is the pipeline. So it starts there, then goes to here. Then you can see there's lines that say that now the image goes from here to this step, and it also goes to this step, and then it goes from this step to here, and from this step to here. So you can see how this pipeline kind of progresses. The way stuff gets in the pipeline is you come up here, there's a palette, and you grab steps from here and you just put them in there. And that's it. And you can try different steps. But the really, really cool thing about Grip is that you can check this little box down at the bottom, see the little eye, and if you click that, then you see the result of the step up here. So you can actually see what's going on throughout the algorithms. You can see intermediate results. And then you can change things like thresholds, like over here, where you can change the hue, saturation, and value parameters, and watch how the image recognition changes on the fly. Okay, so that's what makes it so good, because otherwise you kind of have to do this stuff. You write a program, and then you look at it, and you can't figure out what's wrong, and then you mess with some parameters, and then you look at what happened, and you try and figure out what's wrong, and and it takes forever. So you'll see in a minute that how quickly you can get this working. So here's an example of Grip detecting stronghold. Yes. So there's the castle with the two targets on it. What Opencv does is one of the ways it can detect images or detect features in images is by you can get it to detect what they call contours, which is a kind of closed area around the features of the image that you want. And so here and then you can click this box on the bottom and it colors the contours, so you can see that it found the two targets and colored them. So that's not bad. And then this last step is called filter contours. So it got all this other junk. These were those LEDs that were going down the screen between the targets that you saw before. You can filter the contours, and what we did here is set the minimum area to be 300 pixels. And so that's the minimum size that it will accept as a real component of vision. So it went from finding 16 contours, because that's all this junk on the field, reflections and the LEDs, down to 2 contours, which are the 2 targets that you want. And then what you do is you drag the output of contours to this published contours report, and what it does is it takes all these values, like the center X, center Y, the width, the area, the height, and it puts it in network tables. Okay, so this is an example of where you might run grip on your laptop. So you got the, like Peter said, you got the images through the camera server streaming to the laptop. In grip, you set a source, which you can't see, it's off the end of the picture there, where you set the source to be that camera stream, and then you start doing this stuff. And then the results go into network tables, and so then it gets replicated onto the robot, and you kind of see where things are. Like Peter said, that's a higher latency path, because it's got to capture the image, it's got to send it up, grip's got to process it, it's got to send the results back down, through network tables. So in cases like that, you want to be kind of careful, since it's doing all this like network stuff, about using the camera output to servo the robot to turn, because the images will be lagging a little bit, like from real time. So the robot is turning, and as it's turning, it's seeing images from earlier in time, and so it may not work well. If you put stuff on the RoboRio, and then it's just an Ethernet connection, then it's like really fast. So that's kind of what grip looks like. Here's another example. It's a little bit more complicated. And what is this doing? Oh, yeah, this is from, I just grabbed the images that we took from Lunacy from 2009? I don't know, I can never remember. So here's the images. To give you an idea, it grabs the image over here. So it looks like this, right? So I don't know if you guys were around 2009, but the robots towed these trailers, and the idea was you shot balls in your opponent's trailers, and so you lose by getting the most balls in your trailer. And so what happens is the trailer had a thing on top of it that had like a green over red or whatever color that is, magenta cylinder, and one side was green over red, the other side was red over green. So that's how you tell which one is which. So what's happening here is it takes the image and it looks over here. So it's 2 different colors, right? So you want to be able to do both colors. So what it did was 2 of these threshold operations. So threshold is where you say, just show me the things that have this range of color values, okay? And everything else is blocked. It's like a filter. And so here, we're taking the image, we're doing an HSL threshold to catch the bottom one, the red one, and here's another HSL threshold. The image goes here also to catch the top one, okay, the green image. And then it does some other operations. There's this operation called the road, which takes multiple pixels and makes them into less pixels. And then it does this fine contours thing on the 2 sets of images. And what you end up with is, here's the output of the fine contours. You get this image and this image. And then you send both of those things with network tables to your robot, and the robot says, oh, look, there's a green one over a red one. The aspect ratios are about right. They're on top of each other. So you go, yeah, that must be a target. We'll aim for that. And there were a couple of robots that were like really successful that year, where they would chase people down during autonomous. And this is like like on an ice rink, right? Because it's got the plastic wheels on the plastic field. And so I had seen robots. There's one team in particular in Manchester where during autonomous, robots would start driving away, and these guys would just like follow them and then start pelting them with balls. I mean, it was great, and it was pretty successful. And so that's all from doing vision processing. Now at the time they didn't have grip, and so this stuff was a lot harder to do. But you can see how quickly you can make a pipeline that finds this stuff right now using Opencv and grip. So that's kind of the point of the thing. So the idea is, the way you use grip is you first pick a source. So you say where the images are coming from, and there's a bunch of options. Interestingly, so we can do camera, you can do video. There's a bunch of other options for inputs. one of them that's really interesting is you can point to a folder of saved images. So that's where you take this stuff at noon on kickoff day, and you grab the folder and you say, use all these images, okay? And I'll do that in a minute with the set of images from some year, Steamworks, I guess. So you do that, you create the processing pipeline, and then, then you put the results in network tables, and then you're good to go. So one of the things that's interesting with grip is that you can run grip like on your laptop at the driver station if you want, but the other thing grip can do is generate code, and it can generate code for a bunch of languages. So you can generate a C++, Python, or Java Opencv program that you can then put either on the RoboRio or you can put it on a coprocessor. And for next year, what Greg will talk about is how you can generate code from grip and stick it on the Limelight. So lots of good options there. So the results, I mean, in 2017 when it came out, there were like some, huge number of downloads. We added code generation, and people were playing with, it's not done yet, but we're playing with adding GPU acceleration so that the GPU accelerated version of Opencv has slightly different function names and stuff and works a little bit differently. So we have to change the code generation to be able to take advantage of that. But if we, a lot of teams are starting to use, like Peter said, using these NVIDIA Vision coprocessors and throwing them on the robot to get really, really high frame rates and really good, fast image processing. So we're trying to be able to accommodate that kind of stuff. All right, so I'm going to do a demo, and for this I need my laptop. Okay. I have a Mac, so I have a bag full of dongles. Make this work.
Yeah.
Okay. Oh, is this thing? Where does this go? I gotta get on the other side. That's over here. Okay, this could work. It takes a little bit longer when. What's going on? Oh, there it goes. Just got it. Okay. All right, let me do this. I'm just going to mirror the display. So, okay, here we go. So here's grip. So you just install it. Like I said, it runs on Macs, obviously. It runs on Windows, runs on Linux. So we're not, we go out of our way for all the tools which we develop. We try and make them be cross-platform so you can use it on whatever you got and whatever you're most comfortable with. So I'll start. Oh, that's the installer. Wait, wrong thing. All right, so here it is. So what I'm going to do is pick a source, add source, and I'll pick images. But you can see there's all these other sources that you could use. And somewhere here on the desktop is, LED boiler. So these are pictures of the boiler from Steamworks. Do you know how they had on the big steam pipe thing, there were the red the retroreflective tape things around it? So I'm going to use that. Okay, so there's the image. So I got the image source selected. And what you can do is if you click the little eye thing, it turns it on. And then you can go through the images, and you can kind of see what it looks like. So this is what this stuff looked like. It was pretty, I don't know. I mean, we shot these at, in Manchester during the kickoff. You can see it's kind of messy. I mean, there's lights in the background. There's all kinds of stuff going on. But the thing that makes these unique is that the boiler stuff is, it's like the red ring light. I mean, a green ring light. So the only thing that's green in this image are the stripes. And the other stuff you can kind of get rid of. So what we'll do is, well, first thing I want to do is, it's a kind of thing you might do is like resize the image. Size, resize, there he is. So I can do like a CV resize. So I can take this, the output of this, and stick it to the input of this one, the source image. And then I can do, and I'll make it like half size. Okay, so it's doing like, this is the kind of thing that you would do with like a webcam, because you don't want to. And then I'll turn on this one. Okay, so now there's the half-size one, and so you can see both of them. So you can see exactly what happened after that operation. And I'll turn off this one. There's no reason to look at both of them at the same time. Okay, and now what we're shooting for is we look at this and we go, oh, it looks like what we got to look for is these green things in the target. So I'm going to do a threshold operation. And I'm going to do this. There's different color spaces, ways of representing colors, and so you can read about this online. But one of the things that we support is HSL threshold. So I'm going to take this and wire it to this filter, okay? And you can now independently adjust. I'll turn it on so you can see it. I'm now going to independently adjust the hue, saturation, and lightness, or luminance. And so what you can see is these things. This is the range of values that are accepted in the image. So right now, like, everything is there. So all you see is all these like white pixels, because everything is part of the image. So you want to start narrowing down the stuff which is displayed. And so maybe I'll start with the luminance. Okay, and what I can do is, oh, look, stuff's showing up. Oh, look at that. I can now just see the targets appearing. And now I can, let's see, maybe look at the hue. So I'll narrow the hue down. Oh, that's getting, oh, actually, I was backwards. Wait a second. Wait, let me do that again. Actually, maybe I should start with the hue. What we want is the only thing showing. Wait, where is it? I just did this. Wait. I thought it was here. Oh, okay. So there's the target. We still have those other lights. We want to kind of get rid of those. Oh, they're starting to go away. And all that's left is a target. Now we can look at changing the saturation. Oh, that's making that stuff go away. Let's try coming in from this side. Oh, that makes the target go away, so you don't want to do that. We can do a little bit more here. Oh, the target's starting to disappear, so we kind of want to keep that. Now we can try changing the hue a little bit. Oh, that made the target go away. We can come in from this side. Oh, and that's making most of the rest of the junk go away. So all that's left now is the target, or most of what's left now is a target and some dirt on my screen. I don't know, I can't tell which things are pixels and which thing is the screen. But that's, oh, question. Yeah, well, so sometimes you can, sometimes you can't. I mean, because the colors, the stuff is really good. Oh, that looks horrible. It looks much better on, it doesn't look like that on, it won't look like that on your laptop screen. Yeah, I mean, you might be able to do that, and maybe we could do that, and then try and translate things to be, because then you can still stab the thing. Yeah, as a starting point. It's a little bit hard, because these are filters, so you pick one pixel, and it will, and maybe it knows exactly what the parameters are for that pixel, but it doesn't know what to eliminate,
Yeah, and it's important, as Brad has a whole folder of images here, to go and check all the rest of the images, so.
Yeah, so.
Just get like return values,
Yeah.
So we got this. This looks like it's working okay. I'm just going to keep going, right? The next thing I want to do is look for contours. So I can either just go look for like feature detection tab and get rid of this, and like here's, where's find contours? Filter lines, filter contour, oh, find contours. So I'll stick this in, and then I'll take the output of this image, and I'll put it into the find contours thing. Okay, and now this actually starting to look for features. So if you look at it, it goes, oh, look at that. It found 3 contours. I'm not sure why it's 3, but maybe there may be another pixel somewhere, errant pixel. So now we can filter it based on like the area of the thing which it found, of these contours. So we can do filter contours, and we can turn on this one. Okay, and so now we can just look at the find contours and the filter contours. oh, this found 0. Oh, I didn't wire it. Yeah, so I gotta take the contours and stick it into the filter. Okay, and it's got these 3 contours. Right now, it's allowing basically everything, but we can say, oh, let's look for a minimum area that's, I don't know, like say 40, 40 pixels. Okay, now it's found 2 contours. Okay, and you say, wow, this is looking pretty good. I mean, we've got this image, and it's found the 2 contours, and I haven't done a backup for a while. An important part of image processing. So we got that, and now this is where it's really good, where the grip stuff really works well, and using those. This is the noon image thing. This is like I got these images. It's now maybe I stopped for lunch. Maybe it's 1 o'clock. Okay, but you can see in like 10 minutes you're starting to find starting to be able to recognize these targets that you think you might want to use for the game. So now I really had a bunch of them because I took all those pictures. So you can start going through multiple images and seeing if it can detect all of them. Okay, so here it says, oh, it found 4 contours here, but after filtering it only found 1. So you can mess with the filter parameters and figure out why. Like maybe 40 was too, maybe we should make the minimum area be 30 or 20. What's it, where am I? Oh, that's 230, wait a minute. Yeah, so now that's found 2 contours. So now it's got both of them, because they're pretty small. We're far away at this point. Now I can keep going. Oh, it only found 1 contour, so maybe 20 wasn't right. So maybe I can do like 15 pixels. Okay, so now it's got both of them. What you're trying to do by looking for this minimum area is try and get rid of noise, like a random LED or something like that, or other stuff that's stuck through the filtering process. And that's it. And you start going through all the images, and you go, oh, let's see, that's 1 contour, but there's only 1 thing there. Maybe we could make this a little bit bigger so we can see what the actual image looks like. Yeah, so here's, after the threshold, there's only 1 thing, so that's fine. So it found 1 contour. It's found 2, found 2, found 2, found 2, found 2, found 1, but there is only 1. Found 2, found 2, found 2. Okay, so you do this. This is like great. I mean, this is like in 10 minutes, you got your first cut at image processing for your robot. And then what you do is go over to the network palette, and you say, network tables publish contours report, and then you drag the output of contours to the network tables contours report thing, and now you can publish the area, the center X, center Y, the width, the height, and the solidity to your robot program. And it just shows up in the robot program. Or in the case of, oh, you really can't see that. Okay, well anyway, it really did say those things. And so in the case of the robot program, what you get is, the robot program can reach in and kind of grab all those results, and you can use it for your processing loop. So, and so if you generate code, you can stick that on the RoboRio or on the Raspberry Pi or wherever you want, and use that Opencv code. So, so that's kind of how grip works. So if you haven't tried it, you should try it. Now, you guys said you had some problems. Does this help? Yeah. Okay. So yeah, you're gonna do that.
Yeah,
later.
I'll do that. Yeah.
Yeah, so Peter's gonna do that later because he's gonna stick the code into a program and make it all work. So that's kind of like how grip works. And what it does. Oh, another question.
Yeah, top level, sort of ungenerated question.
Yeah.
In practice, once you've gotten to a stage like this, can you continue to regard the pipeline as truth and generating code as just a black box, or do you eventually get to the point where you just push the pipeline and then you say, okay, now we're going to manually feed?
No, I mean, I would do all the tweaking here because you can see what you're doing.
Yeah, the pipeline gets generated as a separate Java file or C++ file, so it's possible to just drop it in and replace, like after you've got it integrated with your code, you try to integrate in such a way that you aren't editing the original pipeline file, and then you can just re-export and just overwrite the same Java file over and over again. Yeah, so in practice, you never manually tweak it. Yep.
Yeah, I couldn't imagine, after having the sliders and all this stuff to be able to adjust this thing, to have to go back and start editing this thing and changing numbers manually. I mean, that would just not be something I would enjoy doing. And what you could do is, even, you know, as you get your robots starting to get built, and maybe you build a castle or something with retroreflective tape on it or whatever, you can just stream the stuff back to the driver station or the group on the driver station and further refine the image stuff. I mean, these are our images that we took walking around the field with a camera and a ring light, you know, holding with different heights and further and closer and stuff. Your mileage may vary. That's with our camera. We used like a Microsoft Light Cam or something. It was like first choice. But you know, you have a different camera. It's got different aspect ratios. The lenses are different. The sensitivity is different. You know, like whatever. So you really want to make sure it works with your stuff. This is the starting point. And then I would, when you got your stuff working on your robot, I would just send it up to the driver station and then kind of refine the grip pipeline, and then publish it and stick it somewhere. Yeah.
Do you have like methods in there for like camera gain distortion for pin cushioning or?
There is some stuff where you can supply these camera calibration things. I haven't used it myself, but it's there. And so you can read about that with Opencv. So you can supply a file which has this camera calibration stuff.
Yeah, it's worth noting that that can be pretty processor intensive to actually run on the, so if you're running on the RoboRio, that maybe not, it may start to get overkill for what your needs are.
We found on like the old Canon, you know, shooting at the castle, that if the target was far off, the correction wasn't
Oh,
as precise
yeah,
as
yeah.
close we discovered.
Oh.
And there was pin cushioning going on. And then like calculating distance, if the camera's at an angle,
Eagle is a hard.
pin cushioning would be a good calibration.
Sure. I mean, you know, when I see people, you know, back in the frisbee days, I've seen people shooting frisbees all the way across the field using a camera to aim at the thing. But you have to imagine that the target is like 10 pixels wide or something by that point. And, you know, it's really hard to get good data. So oftentimes you have to use other, you know, cheap methods of navigation to get close and kind of line up and then switch to this
Yeah,
stuff.
or you can, I mean, or you can run the camera at higher resolution and do a region of interest like what I was talking about before. So you're processing fewer pixels, you're cropping the image and only processing this much.
Yeah, and so you're saying, say that again?
So what we do, we saw all the targets we shot in the corner. See the targets. We chose whether we wanted to know on the side one.
Okay.
We use the gyro. We use high-res image, just capture one process it, and use the gyro to gain that.
Yeah, so that's sort of like a kind of a key thing. And like I said, so, you know, if you're running with the thing, like if you're running with your vision processing stuff, say on the laptop, you know, like far away with the network connection, if you really don't want to use the images in real time, you know, kind of circling around. So a really good technique, like you said, is use a gyro. Gyros are really easy. So if the thing says it's 45 degrees this way, then use the gyro to make that 45-degree turn, and every once in a while grab images and then keep going. If you have the camera on the robot, you know, where it's connected with a really high-speed connection, and you got good frame rates and stuff, then you probably can do better than that, you know, and maybe you can use, and so, you know, Greg will talk about this, using the limelight that way. Huh?
Brief comment?
Yeah.
I hate to disagree with the experts, but we use grip to get our code base, and we tweak by hand on the Rio afterwards. And once it's closed, the code is so simple.
Right.
That it's really easy to edit by hand.
Yeah,
It's easy.
And certainly when you come to a first event and they say, oh, you want to go up to the field and do, you know, camera calibration or, you know, whatever it's called now, you know, you may want to go back and tweak the stuff by hand a little bit, you know, like you're saying.
We tweak the smart dashboard on the field on game day.
Yeah, to be able to do that. You know, I mean, you get places like, you know, you're playing across the street at the ball field and it's like sunny, you know, the sun goes kind of cloud and all this stuff is changing. So you may want to do some, you know, you may want to try and take that into account. I understand, somebody told me like 254 was practicing in sunlight, you know, for being one of those two alliances that are playing on the ball field, you know, for this afternoon. So they're tomorrow afternoon. So they're like, you know, they're kind of all set for that.
They know.
I don't know. I mean, they may or may not. That practice they did may or may not come in handy.
Games when you fall back overexposing and then pulling the microphones, we try outside.
Yeah, I mean, so getting the camera settings bright is like way important.
Then they upgrade the access cams and the other
Yeah. Yeah, so I mean, you really want, ideally, you want to make it so the only thing you see, or mostly the only thing you see in the target is the target. You know, which is why that retroreflective paint is so good, and big bright ring lights, you know, high intensity, you know, LED, you know, tail lights are so good. So I would, you know, I mean, the ring lights are like $9 for Handy Mark. I just actually ordered a couple, and so, you know, you stick them onto the front of the, stick them on the front of the camera, you know, surrounding the lens, and it's 12 volts, so you just wire it to something, you know, 12 volts in the robot, and you're good to go. Usually you want to like turn it on and off, you know, so you're not like blinding people with it, because they are pretty bright. So usually people turn them on as you get ready to shoot, and then it flips on, and then you get going. Another technique, I've never tried this, but somebody was telling me about this, is that you can like pulse the camera light or something, and then kind of look for things which are pulsing. And then so the only thing that you'll see is the target. And all the other light sources, which are constant, like windows, you can get rid of, you know, because they don't appear in, you know, so you can do stuff where looking at successive frames and figuring out which things are coming and going, and then, you know which stuff's the target. It would be an interesting thing to play with if you guys, you know, wanted to try that.
Specifically on that,
Coming from the medical field, we use that, and it's called image subtraction.
Yes.
Literally, you're taking two images, and you're looking for the difference between the two, subtract one from the other, and the only thing remaining is that point of interest.
Yeah, and so those operations are supported by Opencv and they're on the grip palette. So you can take two images, you can do arithmetic operations and logical operations, comparing the pixels from both images. And it's something, you know, another example is, you know, if you want to find the arc of like a ball in flight, you know, and you get successive frames and you subtract it, you know, the thing you see is everything else is there in both images except for the ball, which move from here to here, and then you can end up with an image which is just the wall, and it's really easy to do that stuff. So it's fun to play with. I mean, just try it. You know, go play with it. You know, like whatever. We were going to do orange hats or something. You know, so if you needed an FTA or an SCSA, you could like get your robot to find one for you.
Drive towards them, yeah.
Yeah, and then shoot walls at them. I think that was probably, let's see. So, okay, any other grip kind of questions right now? All right, so the next thing we want to do is, so Greg's going to talk about the Limelight, which a lot of teams are using. And one thing that's particularly interesting about the Limelight is that for next year, he's going to make it so you can create grip code and send it to the Limelight. And so we'll let him go.
How do I plug in the?
Oh.
Sorry.
Okay, so you need, VGA. Do you have VGA?
This thing here?
Yeah, that's it. Can you see it from there?
Speaking of orange hats.
Yeah, this goes like here.
Yep.
Oh, here, do it. Here.
Upside down?
Nope,
No, it's right.
it's just
Oh, it's
really,
bent a little bit.
it's really bent a little bit. There we go.
Yeah, I wasn't getting it in there. Oh, do you? Oh, let's see. I don't have the slides.
Oh.
I guess I can. I guess I should show the slides.
You want to show the slides first?
Sorry. Oh, okay.
All right. There we go. Is that,
Okay.
Yep.
So, yeah. That's
Here, you want to stand here and that way you can talk.
Okay, so first of all, maybe introduce myself. I've been a team mentor for Team 987 for since like 2005. And we did vision pretty much every year that it made sense to do vision. We've done it a lot of different ways. We've done it with coprocessors. We've done it on the CRIO at the time. We've done it on the driver station. We used multiple different coprocessors. We used a Panda board. We used a Jetson. And so kind of over the years, we made vision control more and more of our robot. So it got to the point where our drivers weren't even aiming or even deciding when to shoot. They just say like, you know, we're in the area, you aim and you shoot when you're, you know, like the castle game, our robot had a 2-axis arm, and they would just say, all right, it's time to shoot, and the arm would aim and decide when to shoot when it was perfectly lined up. And I think in our last regional, we went to China and did the summer regional, and it never misaimed a single ball, you know. So like in 2006, we had auto aiming, and we were trying to get the drivers to use, you know, the feature IntelliOp, and, you know, it wasn't good enough. And so like over the years, we're like, we want to get the code to the point where it's better than the human. And so that led up to, you know, by the time we got to the castle game, our robot was so hard to aim, a human couldn't aim it. And so anyway, we've learned a whole lot of stuff about vision and FRC and kind of like effective ways to make it work. And a lot of things were really hard, which like Peter's stuff has made a lot easier. Like even just getting your camera to start up and have the exposure set to what you want. You know, we had to write a custom script in Linux to, when it boots, make sure you set the camera you know, set the exposure low and stuff. So anyway, this summer, my son did 4 years on the team, and then he graduated and he started working as a programmer, and he's like, you know, we're like, we should put this together into something where it's easier to do vision and FRC. So what we came up with is called Limelight, and it includes like everything you need in one box. You know, you've got the solution for how to power it. You just can plug it right into your PDP, and it has regulators and stuff to handle all the noisy voltage on your robot. It's got the lights. You can turn the lights on and off easily. You know, because sometimes we wished we could turn those lights off sometimes because they're so bright. You know, you catch them, you know, at the wrong angle, and then you can't see for a little while. You know, like Peter mentioned, a lot of the cameras are hard to mount, so I was like, let's have it's a square and it has mounting holes. And then we wanted it to be accessible to teams who don't necessarily have programmers. Like probably in here, we've got a lot of really good programmers, programming mentors on your teams. To a lot of teams, even if you give them all the code, you know, we all publish our code every year. A lot of teams still can't like implement a vision system even with all that code. There's just so many moving parts and so many things that have to work together. And then on top of that, we thought about the kind of situations you run into in FRC competitions, like the fact you need to go on the field and calibrate really quickly, because every field might be slightly different lighting conditions. Actually, we got hit by the Houston thing. You know, we got out there in Houston, there's like this gigantic window with sun beaming into one side of the field, and all of a sudden, you know, how do we track the boiler now? So that's you know, a lot of design decisions in Limelight were made based on FRC experience. One of the other big things you have to do when you do a vision coprocessor is how to send the data back to your RoboRio so your robot program can use the data, you know, use what the vision algorithm came up with. And so we made Limelight talk to network tables. It's just a super easy way. Like any beginner team, we've given some of the Vegas teams Limelights, and you know, you just open up this network table, get the X and the Y value out, and they've got their robot chasing cubes and stuff. So network tables has turned out to be a really nice, easy way to work with, you know, make things interoperate. And we made it work with the camera publishing thing. So if you open up LabVIEW dashboard, Smart Dashboard, Shuffleboard, all of them will see your Limelight, and you just pick it out of the list. Let's see. Okay, so what's on Limelight is it's basically a Raspberry Pi based hardware. It's a custom board that has like the regulators and the LED controllers and stuff. It's got a fixed function Opencv pipeline. So it does stuff very similar to what Brad was showing you. You do thresholding, You can pick some number of steps of erosion and dilation. Then you can filter your contours. And then we've got like some crosshair support. So a crosshair is actually a pretty important feature. Like you need to think about how you implement that on your robot, because let's say your vision says the target's at pixel 100, 200. Well, where does your robot shoot per, which pixel corresponds to your robot being perfectly lined up with the goal? So that was one thing we put a lot of thought into in Limelight. I guess I'm going on a tangent here, but the way you do it is you just point your robot at the goal, get it making a perfect shot, and you say, remember that as the crosshair. So then all the values you get back from Limelight are relative to that. So if you get an X angle of 2 degrees, this means 2 degrees off of what you said was perfect. And then some of the years this might come in play in future years, but we've had actually dual crosshairs where depending on distance, it interpolates the crosshair. So in the Stronghold game, that's how we got it to be, basically not miss shots, is like even if we were at different distances, it would just adjust. So it would aim at a different angle. I mean, in that game, our camera was off to the side. So we're shooting this way and the camera's over here. So obviously things change. There's a lot of things to think about there. One of our beta teams said, hey, in Steamworks, there are 2 goals. There's a boiler and there's a gear peg, and we want to be able to do both of them. Like this, we made it after Steamworks, but they say, what if there's multiple goals? So we said, okay, we'll give you 10 configurations. So you've got this fixed function Opencv pipeline, but you can have 10 sets of settings with their own crosshairs, their own HSV thresholds, all that stuff. And your robot can just flip between the pipeline configurations on the fly. So you push a button and now we're in gear peg mode. We also, since we could, we put an extra USB camera on there so you can have like a backup camera. Like our first design had like 4 USB cameras, and you can have cameras all around your robot, but it got trimmed down to 1. So the thing we were gonna talk about today is, this is all nice. It is basically the best vision system we've made for our team, like compared to our team's past systems. But you can do even more. Like some people do different things with grip and Opencv code. That's not necessarily what we did. So what we want to do next year is start opening up to customizability. So what we've done is we've added a code generation step to grip, which generates a script that we can read, and then we just implement your pipeline. So I'll show you a quick demo of that.
Yeah, while they're setting up, I'll just say that if you want to not mess with getting all this stuff, if you want to use a coprocessor, you don't want to mess with getting all the software installed on the coprocessor and making sure that it works and making sure network tables works and all that other stuff. You just want to have a turnkey solution. That's where this really comes in handy, because Greg does all that work up front, and you just get a box with network tables coming out. You plug it into a switch on the robot, and you're done. And then it's just all choosing the right software profile.
Yeah.
So,
this year, when the game was announced, we got our stuff, and we took the cube out, and we had a robot chasing the cube like that afternoon, because you just, the Limelight's basically just designed to plug into an FRC robot, and it sends you network tables, so you tune your pipeline up, and then you're working on robot code. We had kids who hadn't been interested in programming the previous years, going like, oh, I'm going to make the robot chase the other kid who's wearing a vest with a stripe, reflective stripe on it, and they can do it pretty quickly. So first I'll show you what Limelight's interface looks like. So here you've got your, it comes up in tabs here. You've got your input, where you can control your camera exposure, your white balance settings. You can flip the camera upside down or right side up. Then you got your thresholding tab, and this is the new button we've got. This will be, the UI will be updated for next year, but you're going to be able to load a grip pipeline into any of your pipelines. So I forgot to mention pipelines up here. So you've got your 10 pipelines here. Each one of these has a complete set of all of these settings. So let's say we go to, here's the contour filtering like Brad was showing. You can filter by area, fullness or solidity. That's kind of like the ratio of the convex area to the area. And aspect ratio, so if your target's wide or tall and narrow, you can filter those. And then the final one is our output stage. So you can say, once you've found your contour, do you want to target the center, the top, the left? You can, like some games have like the gear peg had 2 vertical stripes. You can treat the 2 stripes as one thing and then say you want to target the center of it or the top center or whatever, stuff like that. So where grip's going to come in is in this thresholding step. That's where we're doing all the image processing stuff. We're going to basically replace that whole block with your custom grip pipeline. So let me pop over to grip. So here's a pipeline I made where this is probably not a good pipeline to use for tracking anything, but it's using steps that Limelight doesn't use right now. So we've got a blur step, just to smooth out the image. Then I used the HSL threshold. Limelight normally uses HSV, so let's use something different. And then an erosion step, and then a fine contour step. So the way we're going to interoperate with grip is the image coming in. When you put the pipeline on your camera, it's going to become the camera image. Then all the steps in between, any of those that generate images, we're going to put in a list for you. So when you switch over to the camera, you can see these images as well. And then whatever the last contour output in the pipeline is, we'll send those contours onto our contour and targeting logic stuff. So your stuff goes right in the middle. The way it works is you do tools, generate code, you say Limelight, you give it a name and a folder. So let's go. So that just generated the code. And we'll come over here and we'll say upload a grip pipeline. This is the pipeline we just generated. And then we can switch between whether we're using the built-in one or the grip function. Oh, it didn't work. Oh. Okay, so here we go. We just got this functionality working like 2 days ago or something, so I think there was a bug there. So this pipeline number 9's got it loaded. And so here's the input image, and then there's the blurred image, and thresholded. It can't see anything because of the thresholds, and then the final output. So anyway, that's the idea. We're gonna, so then you can use grip to kind of tune all your settings and then drop it in here. So I guess that's pretty much the demo. If anyone has any questions, I can. Sure. Oh, it's the Limelight's $400, but that's all the hardware and everything, and there's no, the new features are free, of course. Okay, so Limelight processes at 320 by 240, and that is, we found that to be sufficient for all the FRC targets we've had. And we did a lot of stuff with that on the frame rate. It's running at 90 frames a second. And we actually use, the camera output directly. So we just feed the export into PID list and aim, so we had good luck with that in both Stronghold and Steamworks. So yeah.
Sure, you were feeding that into the bits, you're using that at real time.
Yes, yeah, so it's generating the updated X and Y angles and feeding, the values go right in network tables. The RoboRio code is reading that network table's value and using it as the sensor value to a control loop. And we did a lot of work to minimize the latency between when the photons hit the camera to the network table's value is updated. And that just makes stuff easier. Though in a lot of cases it is useful to also feed your vision solution to a gyro and aim. It just depends on,
So fortunately, we ran out of time a little bit. So instead of doing the demo here, I'll talk about the demo. And what we'll do is we'll have the demo down in the WPI booth, down in the Robot Service Center. So folks can come by this afternoon or whenever to see it. Basically, what it is so I've got a couple cameras hooked up to a Pi 3, and the Pi camera is also supported if you want to plug in a Pi Cam. That works too. We do have an image that we'll probably end up distributing next year, which is it's an image for the Pi that has a read-only file system, so it's safe to like yank power from. It doesn't, so that way your image doesn't get corrupted. And for demo purposes, we built a pipeline, built the processing pipeline with Eclipse, and we just export from grep a Java file and load it into that. And you can deploy that with generated code, just copy it over with SSH, and I think this is an area where we'd like to make some progress on in future years in terms of the ease of use, of making it easier to use the Pi type of coprocessor. So speaking of future plans, so one of the things is that, again, kind of easier deployment mechanism for vision code, particularly from grep. I mean, things like what you're doing with the Limelight is exactly like that. It's like, hey, let's get these tools to talk together more easily, to make it easier for teams to use. As before, I mentioned the camera support for Windows and Mac for USB cameras from Camera Server. And I do want to make some web dashboard improvements. So that little web page we popped up is a very basic web page. I coded it in about, I don't know, half an hour in terms of level of complexity. So I'd like to get some more in there, setting the video mode, changing the resolution, compression, FPS, display some statistics on there with regards to active streams. So things like, how many camera feeds, how much bandwidth am I using, what resolutions are they getting streamed at. Sometimes you don't necessarily know what your dashboards are doing, or you kind of have questions about how much bandwidth is used. We try to show that on the dashboard side, but it's useful for debugging purposes to show it on this web page as well. The other thing is, I know that a couple teams have run into bandwidth problems this year using Camera Server, primarily due to, what happens is Camera Server always prefers, if it has a JPEG image, it will use it. So if you are running the camera in JPEG mode, and so the camera's feeding a JPEG image, it's like, oh, I've got a JPEG image, it's the right resolution. If I've got a dashboard trying to pull that JPEG image, I'm going to ignore whatever the dashboard is telling me to use as a compression ratio if it's the same resolution. Now, if you change the resolution, it's going to recompress the image. But the idea with that was to minimize CPU usage on the RoboRio. The downside is that it means that sometimes your bandwidth, depending on the camera you're using, might be a little higher than you expect. So the camera's feeding a JPEG image that's at like 85 or 90% compression, and there's no way to get it to be a lower compression without also resizing. So that's something we'll fix for next year. And as I mentioned earlier, doing some stuff with persistent settings, making it easier to save and load camera settings from both the web and the software side. And I think that's it, Brad.
Yeah, what was
There's one more slide, which is the ultimate simplicity.
Oh, yeah, go ahead. Yeah, do that.
Brad likes the slide.
Well, you know what it is? So, we keep trying to, put these cool targets on stuff and try and do good computer vision stuff. We do these talks, we write all this software, that kind of stuff. And like in Jurassic Park, when the guy said, the dinosaurs are all female or something, so you can't make, new dinosaurs. And Jeff Goldblum says, life always finds a way. Well, here's the latest for Andy is the photon cannon, and I think that's what it's called, and it puts this bright light you know, so it's fixed shooting distance, you know, fixed geometry and all that kind of stuff. So people always try to find these really cool ways of doing stuff that kind of nice computer vision. But you guys are here and you're learning about this stuff, so I hope that you'll feel challenged to try and make that stuff work. And
Photon cams don't work in auto.
yeah, so yeah, more of the shoot auto. You're gonna have to shoot more of the photons and make it work. So yeah, thanks for coming. So like Peter said, we'll be down in the road service area in Building Palette next to admin. And I'll do a plug. My Apple Watch says at 12 o'clock we're going to be in 30. Where are we? We're in 305. We're going to be next door in F, wherever that is. You know, and talking about WPL futures and stuff. So contact for that if you want to hear about it. So thank you. And see you tomorrow.